Okay, well, welcome back to this lecture series. So we'll continue with where we left off. This is going to be stress-driven nanostructures in ceramics. So, this is obviously nanostructures by surface modification, and we talked about the surface modification by gas phase reaction. And today I'm going to talk about another technique that is actually, we can create surface patterning or surface patterns by strain-induced nanostructuring. So I give you some references if you want to read more about this. This work actually started with some work that we were doing in field cell. On a yttrium stabilizer zirconia substrate, gadolinium doped cerium oxide was deposited by sputtering a thin film of the order of 270 to 360 nanometer. And then it was heat treated around 1150 degrees C for about 10 hours in air. And you can see that the film actually broke into nanofeatures and created the so-called nano-islands. So if we take a closer look at the nano-islands, a remarkable size similarity, and also we see some sort of alignment. You can see that they're ordering sort of some self-assembly type scenario, where we find that these nano-islands are aligning along the softest elastic modulus direction of the substrate. And then if we do a cross-section, fibbed cross-section in TEM, so this is a cross-sectional nano-island. You can see the top surface is the 001, same as the substrate. By the way, both are cubic fluorite materials. So same crystal structure, so top is 001. On the inclined plane is 111, and actually it should make an angle of 54.7. So in TEM, we can actually measure that angle to confirm the crystallography of the nano-islands. In terms of composition, there is some solid solution or dissolution of the gadolinium doped cerium oxide into the substrate. So there is some redistribution of composition. So it's YZ near the bottom here, and gadolinium doped cerium oxide on the top. And then there is some intermixing of yttrium and gadolinium and cerium in between. So there is some solid solution of the deposited film onto the substrate. So again, cubic fluorite structure, we know that calcium actually makes face-centered cubic type of arrangement, and fluorine makes the simple cubic type arrangement. So it's a calcium fluoride type structure. That is the fluoride structure. And because of the charge variation between the cation, which is divalent, and anion, which is univalent, that calcium goes into every other cube because of the charge imbalance, calcium and fluorine. So is this a de-wetting? If you put a thin film, your film can de-wet based on the condition of so-called surface and interfacial energies. That thermodynamically, the Gibbs free energy of the broken up film is lower than the Gibbs free energy of the intact film. If that's what the condition is, then the film is going to break up. And this is known as the so-called de-wetting. So the question is this simply de-wetting? And we know that there are examples of de-wetting. For example, this is the SEM micrograph de-wetting of this 123 superconductor yttrium barium copper oxide superconductor thin film that was deposited on lanthanum aluminate single crystal substrate. And you can see that the film is breaking into features, and there is no size similarity and there is no regularity in this film breakup. Here is another example of SEM micrograph showing de-wetting of strontium zirconate thin film on a strontium titanate single crystal. And again, you see that there is no really size similarity or any particular water in this wetted films. So, de-wetting typically will create nanofeatures, but a size similarity and a special order is typically missing. So is this then so-called ATG type instability? ATG type instability is created by competition between the strain energy that is created in the film during deposition, and then that strain energy is minimized by creating new surfaces. And this is known as, in the semiconductor community, it's known as ATG type stability, and people have seen this is very common in silicon germanium, indium gallium arsenide type systems. And the other thing that people see in thin film semiconductor is that significant strain can be developed due to lattice mismatch between the film and the substrate, and Stransky-Krasnov type growth mode, which is, people see in semiconductor thin film, which is simply layer by layer film growth followed by islands. You grow multi-layer thin film, beyond certain thickness, the film will actually create nanostructures, and they will order. So is this ATG type or Stransky-Krasnov type? It's interesting that, again, we don't see in ATG or Stransky-Krasnov type SK type growth, we don't see again special order and size similarities. We have to really guide to get orientation and ordering. You can guide them by growing multi-layer film that we'll talk about, or you can define lithographically mesas and then deposit your film, or you can introduce dislocation arrays in the underlying substrate that will organize the features, or you can deposit on vicinal or miscut substrates that can help guide the order. Okay, with that, let me show you some examples. So this is the multi-layer example. So this is, you can see that this is deposition of this single crystal silicon germanium on silicon, and AFM image, so of the single layer. You can see that there are features but no particular order or any alignment. But then if you do this bilayer, 20 bilayers, keep on building this multi-layer, and then you start seeing some ordering. So this is the example that you can guide the order, which is disordered kind of here, and then by going multi-layer, eventually beyond certain layer, you get some ordering. The other example was the BSA, so you can photolithographically define, create well-defined structure, and on top of that you deposit your germanium islands, for example, on mesas that was created on 001 silicon. Here you can see examples of that, So you're guiding by creating this photolithographically created pattern on the substrate already. Or you can guide by introducing dislocation loop. You can see these are dislocations. If you take a closer look at this, at this pattern, you can see that they're very well ordered. So you can, get alignment of nano-islands along dislocation network. So that's an example of that. And so initially, my student Rauscher actually proposed that what we're seeing is an ATG type that gadolinium doped thin film deposition essentially modifies the substrate surface composition by solid solution, and it creates a stress layer, and that leads to surface breakup into islands to relax the strain energy. So that was initially, so the immediate question was, does the surface need to be pre-modified? So during deposition, do you need this solid solution, some interaction between the film and the substrate to happen during deposition? And then Ansari, who actually created, instead of a thin film, he deposited GDC by lithographic patch. So instead of putting a blanket film, he created lithographic patches that I'll show you, and then deposited GDC there. And then did the heat treatment around 1150 degrees C, and he saw that these nano-islands are forming using that lithographic patch as a source, and it spreads by surface diffusion. So you can see that these are the gadolinium doped cerium patches that were deposited by photolithographically defined holes. So this is where GDC is deposited, and then after the heat treatment, you can see this part of the GDC patch. You can see around it, you're forming these nano-islands. The closer look shows the nano-islands. Again, you see size similarities in the order. And again, if you cross-section and study the crystallography and composition, it's exactly the same that was originally observed on a blanket film. So clearly, this is, you don't need this solid solutioning during the deposition process, but it can happen during the high temperature heat treatment, where material can spread by surface diffusion and the nano-islands form during the heat treatment process. Sometimes we have seen that away from the patch, so this is the source, see nano-islands, but then suddenly we see some of this stray island colonies. So the surface diffusion is happening, but it's nucleating here, not in between. So there must be some defects or something there that promotes the nucleation in that location. So moving along, so then, my student Ansari said, if we can do this by depositing GDC in this isolated patches, why not deposit it from a powder suspension? What it does is it takes powders of various oxides, put it in a water suspension, creates a water suspension, puts a few droplets of that suspended particles on the substrate, and then dries it out and heat treats it. And then he found out actually that you don't need all this, sort of stress created during the deposition. In fact, some modeling was done by another student from our group, by a face field model, very interesting technique to do microstructure evolution modeling. The deposition stress actually proven insufficient to drive the sustainable or island growth. What we found is this solid solution during which, because of the size difference, this critical strain is created that drives the process. So this is the process that I described, that takes powders, creates a water suspension, put a few droplets on the substrate, and then dried out and heat treated. So this bypasses all the complexity and makes the process very, very simple. So we can, that has added flexibility. We can test all kinds of powders or source material and all kinds of substrate. So you can see the powder-based technique actually works very well. And it, you can see the remnant powders, but you can see nano-island forming around the source powder particles. Here you can see intact source powder particle, a lot of agglomeration, but wall-to-wall nano-island forming around the particles. And if you do the chemistry and crystallography on this nano-island, it has the exactly same chemistry and crystallography, and they align along the 001 direction, softest elastic modulus direction of the substrate. So this is very interesting. So does it happen with gadolinium doped cerium oxide only, or can other source material? And what we have shown that other rare earth oxide will work. So this is gadolinium oxide. You can see gadolinium oxide nano-islands around it. Europium oxide nano-islands around it. This is samarium oxide nano-islands. Terbium oxide is the source, is part of the source, and yttrium oxide, you can see. So this is very robust. If you take YZ, single crystal substrate, and put any of the rare earth, it works beautifully. So another question that we wanted to address is that, is the nano-island forming during annealing at high temperature, 1150, or is it being nucleated during cooling? And to do that experiment, to illustrate that, we found out actually it's happening in the at the high temperature heat treatment process duration. So this is again the slow cooling. You can see remnant particle nano-islands by just slow cooling. And then we did an experiment where we put the powder source material on top of the substrate, and then we anneal it, we hang it platinum wire, and anneal it in a vertical furnace, where after annealing, we actually cut the platinum wire and open. There is a door at the bottom of the furnace, and the sample quickly drops into a bucket of water to do quench, to do heat treatment, and then do water quenching. Obviously, during quenching, this is a ceramic material, so the substrate actually shatters. And amazingly, you can see that shattering actually cuts the nano-islands, cuts into the nano-island. So clearly this, quenching experiment is proving that these nano-islands were formed at high temperature treatment. And then the other beautiful thing about this shattering experiment is that the sample is shattering along the softest elastic modulus direction. That actually reveals the orientation, alignment direction of the nano-islands. So with that, I'm going to move on to basically the key requirements of that The substrate should have high elastic modulus and isotropy. They should choose substrate that has very high elastic modulus and isotropy. The higher the anisotropy, the better the alignment. The other requirement is that your substrate should either be a single crystal or have highly textured surface so that the orientation is preserved. And then the third requirement, an important requirement, the dopant of the source material that we are putting on top of the substrate should have some solid solubility. In fact, we believe is that during the solid solubility or solid solution process, that the critical strain has been created by the difference in size of the dopant in the substrate. So then we looked at the effect of the change in the orientation of the single crystal. So remember, so far we have been doing on 001 YZ. What if we take 110? So again, we take a 110 substrate and we put this source material in lithographic patch, or we can put it in powder form. And then you can see that from the source, you're forming this oriented nanobars. If you take a closer look, it looks something like this. Very regular, it's about 90 nanometer width with about tenths of nanometer of space in between the nanobar. So this is an interesting change in the orientation, actually gives this nanobar type structure. So we did powder-based process. So we deposited patches by inkjet printing. Remember, inkjet printing is more precise deposition of the source material compared to screen printing. And then we looked at the various locations. And in some location we saw, so this is source, inkjet printed particle assembly, and we see the nanobars forming vertically. Source, in some other location, we can see that the nanobars are actually spreading with an angle. Okay, so we actually decided to create this angular, angular dependence of this pattern spread. So the spread is from the source up to maximum spread length. So that's your X. And the angle is the so-called angular dependence, how the nanobars actually spread. So we do a polar plot, and we can see that there are, so this is spread, extent of spread along the easiest direction, or 0 degree theta if you wish. And this is the other axis, the slowest spread direction. So if we actually plot the square of this extent of growth as a function of time, along the max in this direction, 0 degree, theta 0, and along the minimum, where theta is 90, for example, we see actually a linear correlation. So this seems to indicate this parabolic kinetics or the spread of the extent of the nanobars as a function of orientation angle. That's interesting correlation. Then we looked at the effect of the vicinal surface, that if you intentionally cut the substrate and create a miscut sample. So we, used two types of miscut samples. Type 1 was 001 YZ, miscut about 110 axis by 2 degrees. You can see that miscut angle and orientations are defined here. So this would be alpha would be the angle by which it is miscut about certain axis, x. So this is alpha angle about x direction. The type 2 was again 001, substrate miscut about different axis, 100 by 10 degrees. So we use this 2 miscut sample. Initially, you can see the AFM image shows that the steps are not well developed in as received sample. So we do heat treatment now. After heat treatment at 1250 degrees C, we can see the steps are well developed. And you can see the AFM three-dimensional picture of AFM shows these steps well developed. Steps in terraces and terraces and steps and so on. Type 2 doesn't look as sharp. So the type 2 is here and type 1 is there. And again, you see the definition of type 1 and type 2. So 001 substrate miscut about 110 by 2 degrees. And again, 001 oriented substrate miscut about 100 by 10 degrees. So this is sharp, this is not as sharp. Now we put our source material on this miscut sample, and you can see, so that's the source, and then we heat treat, and you can see nano-islands are spreading long distance. So this is really amazing that we actually are enhancing the border over longer distance. And we see actually in this case, European oxide is put, and you see nano-islands. And then if we go further distance, we see nano-bars, which actually eventually will chop into nano-islands. And we can see nano-islands actually form along the steps. So these are actually nucleating along the steps. So the steps that we create intentionally actually helps form the nano-islands. Looking on the type 2 miscut sample, you can see here that source is around here. So as you move away from the source, so you see some features here. And then if you move further away, you simply see the steps. So there is no nano feature formation. And in fact, in this case, we see actually a zigzag type arrangement. In this case, kind of hexagonal pattern you can see, and the nano-islands actually form on the step corners. So what we're doing here, so if you look at the different location, so these are the source material that were deposited by inkjet printing. So location A is far away from the source. So you can see location A looks like nothing is happening. You just see these steps. And location B is very close to the interface between the particles and the intact substrate. And you can see it looks something like this. So you see this sort of hexagonal pattern. And then moving further away, you see these steps. So, what we see is that as we heat treat this, type 2 misoriented sample with the source material on it, the source material is actually modifying the steps. It's actually sort of doping-induced faceting of 100 steps that decompose into 110 segments. It creates this out-of-phase type arrangements that you see right there. So, so this is interesting. This is actually the doping-induced faceting. So this can be a new way of creating patterned surface on your substrate. Then we looked at the environmental effect. First of all, if you just cerium oxide powder on YZ and do it in air, it doesn't form the nano-island very well. But if you heat treat it in 5% hydrogen, 95% nitrogen mixture as a forming gas, you see the nano-islands showing some well-ordered pattern compared to random behavior here. So then we looked at the size comparison. So if you look at lanthanum and compare size of cerium 3+ and cerium 4+, cerium 4+ is much lower, smaller than lanthanum. So the picture that we are seeing here, this is exactly what you see kind of a nano-island formation using lanthanum oxide. And if you look at the cerium 3+, has very size of lanthanum oxide. So what you're doing that in this reducing environment, you are converting some of the cerium plus into cerium 3+, cerium 4+ into cerium 3+, and that's giving you the right size to get the effect that you see in lanthanum oxide. So this is known as, Al-Chemy by environmental effect. You're basically changing cerium 4+ to cerium 3+. That promotes the ordered nano-island formation. We looked at the effect of, air, argon gas, and hydrogen, nitrogen. So this is in air. You see the extent of the nano-island formation. This is in hydrogen, nitrogen environment, pretty robust. And this is a different magnification, but in argon. So argon and air looks very similar, although this is a much higher magnification. You can see the error scale bar there, 2 micron versus 5 micron. But in hydrogen, nitrogen, it's much more robust. It's well spread. And so what we found is that the coverage is maximum in hydrogen, nitrogen, then in air, and then least amount in argon. And then we looked into extension of this into alternative substrate and source materials, and compared with YZ, we found various possible substrate, including spinel and a lot of other materials. And then we looked at their elastic anisotropy. They compare very well with YZ. And then we looked at the availability of their single crystal, and if they're available, how expensive or how reasonable priced they are. And based on that, we found out that these are viable systems. You can see nickel on copper or copper on nickel should work. And also many of the oxides on a spinel should be viable route to do this. So we looked at nickel powder on copper, and you can see, so this is nickel on top of copper, and you can see some features forming. And take a closer look, you see the clear features. This rectangular 4-fold holes are created by this Kirkandel effect because of difference in interdiffusion rate or in diffusion rate in copper and nickel. So in this case, your copper is diffusing into nickel and creating this hole. Then we looked at copper on nickel substrate. These are copper on nickel substrate. We see some feature. Higher magnification shows the features, and you can see that the features seems to align around surface defects, if you wish. Surface had some roughness, and it aligned along those defects. So we are not getting as beautiful a structure as in YZ rear arc system, but there is some hope. It's copper, nickel, and perhaps in the spinel system. With that, I'm going to move on to something else that we create this nanostructure, some very hard inert material like ceramic. If they don't have any interesting optical or magnetic or electrical properties, what useful are they? So we said, can we transfer this pattern onto soft materials like polymers? And we showed that by so-called replica molding, we can transfer the pattern. So you cast a soft polymer on top of this, cure it a little bit, and then peel off. And you can see this nano-islands have been transferred to this PDMS. And we actually showed that you can transfer the nanobars as well. So this is YZ110 astomolar nanobars and PDMS replica. So it's in high magnification. This is on YSZ, and this is on PDMS by replica molding. You see some dislocation where the nanobars actually contact each other, some deformation. So then I'm ready to summarize. Strain-driven instability can be used as an affordable manufacturing technique to pattern surfaces. Process has become very, very simple. You can do it by sprinkling source powder onto the substrate, followed by annealing in high temperature, and applicable to a wide range of materials. The most two important criteria is the substrate with a strong elastic modulus and isotropy, and a source material with limited solid solubility in the substrate. And then what we discovered that we can do this doping-induced faceting opens a new avenue for surface nano-structuring or pattern. Remember that these doped surface where these 100 steps were decomposed into 110 type steps. So we were actually modifying the surface patterns. And by replica molding, we're able to transfer this to soft materials like polymers. And then this pattern polymer would have interesting viscoelastic behavior and mechanical behavior. So because these are now aligned spaghettis, if you wish. So it would have interesting anisotropic mechanical behavior. And if you're using electronic polymer, it would have anisotropic electronic or electrical conductivity. So with that, I'm done with this lecture, and I'll see you in the future lecture.